to unified conferencing.
Terrible. But no, just a warning. What are you trying first? What are you trying? What's the difference? My hypothesis is it's not going to work because I ran an experiment and it didn't work. So the issue is basically you look it up, you get with EMAP, you get test TDS scrambling. And okay, so that's still a little bit of oh, what? No, I was wondering, like, with cooked up DMAP, acetic anhydride conditions where you get scrambling, is combined yield of scrambled and unscrambled product like okay, or is it still terrible?
In general, no.
And you said you used LHFDS to delete
No reaction. But how do you solve scramble?
Yeah. But that's still unsolved as well.
So 58 up to 100.
Oh, right.
It's just
Have you considered like attenuating the nucleophilicity of your activating agent, like paramethoxypyridine, for example? Let's use that. Just grasping it, like if you're trying all the stuff more random.
yeah, but like it's plenty of fiber stuff, right? I thought we were using 2-methyl EMAC, but no one used it for
Can you adjust the camera to the next board?
I guess we have a couple minutes before we start. Did the TAs tell you about the lectures that are having next week? So the good news is we've got Martin Eastgate making a surprise visit for lecture number 20, which means you get a much better product than you normally would. And then for lunchtime, we will serve what? Pizza or something? Or sandwiches, something like that. Do you guys have a preference? Florida, maybe we can send them a gift certificate for some snack or something. It won't be lunchtime your time. Pizza, sandwiches, anybody?
Regent's always great.
Regent's Pizza? Do you guys all like pizza? Okay, maybe let's make that happen. So Rick Ewing will teach us about patent law in medicinal chemistry. So I touched on it for like 5 minutes during the course of the whole class, but now we get an actual expert to get you ready. Patrick, how much of your day do you think about patents?
I like to think about it as little as possible.
As little as, yeah.
Send it to someone else. It's definitely something that you have to
Yeah. Depends on the company. Some companies, you might spend, after your series is done, you might spend months just working on a patent. So hopefully that saves you time. And then, so yeah, Martin for lecture 20, so no change in the time, 8 a.m. And then lunchtime free pizza for patent law. And then I guess the midterm is the week, or the final is the week after that, right? Which is going to be loads of fun. So that means today really is probably the apex of difficulty. Covered some pretty difficult things last week, but today pretty much covers the rest of what you need to know to become heterocyclic master. The lectures after this will cover the greatest story in medicinal chemistry and history, and then thinking about how alkaloids are made, because that's kind of important in certain contexts. But it doesn't involve a huge amount of nitrogen content, because nature doesn't make a lot of heterocycles of the type we'll talk about today. So we've got benzodiazepines, alkaloid biosynthesis, Martin Eastgate, and then the final. So with that, let's begin. Lecture 17, we're going to cover the higher order azoles, the ones we didn't cover before, the triazoles, the tetrazoles, the ones where you start mixing and matching oxygen, nitrogen, sulfur, oxadiazoles, thiadiazoles, bridged heterocycles. Let's talk about 1, 2, 3 triazoles. Of course, at Scripps, we know the best way to make them is through click chemistry. But the other way to make them that's kind of useful if you're making, as you'll see in a little while, benzanulated versions of these is to think about the diazo compound or oxidative events that we'll see later on. But in usually it looks like you've got an alpha diazoimine, which some of you may remember. Actually, if you have a sulfonyl group here, that can be a masked version of that. So you may remember Falkin and Gevorgian published many years ago a method. If you've got a sulfonyl triazole and you heat it up, it can actually go to this. It's sort of a nice masked version of an alpha diazoimine. And in the forward sense, if R3 is not a sulfonyl, you can push that to it'll cyclize spontaneously to triazole. So there's not much in the way of case studies for 1,2,3 triazole, especially at Scripps, because we all know how to make them. But the 1,2,4 triazoles are a little bit more tricky. And the canonical way of making them, if there's no real substitution around the nitrogen that you have to worry about, is taking a nitrile, treating it with hydrazine. That gives you your favorite amidrazone. And the amidrazone can then be condensed with ester, or you can do an EDC coupling with the acid, followed by in situ cyclization. But the amidrazone and a carboxylic acid oxidation state moiety condense to give you your 1,2,4 triazole. Now, when you start having R groups here or here, that's when things become more tricky. And so a number of useful methods have been invented for achieving this. In the case where you have R4 equal to a substituent, probably the go-to way of doing this is in the case where R1 and R2 would be H. You would just take the diimine shown here, derived from hydrazine, add it in, and condense. In the case where R3 is your substituent that you need to worry about, then the go-to method is either going to be a condensation onto the thiomethyl compound or onto the acylamidine. And the acylamidine is a useful method that came out from Genentech a few years ago, published in a nice JOC paper. The key to remember here is that the NH2 will exchange with the NH2 here under acidic conditions. So the procedure for this method involves taking your amidine, derived from a nitrile, and treating that with the acid and EDC, and then 10 equivalents of acetic acid and heat, and your hydrazine will exchange NH2 for this NH2, and the R3 group will end up right here. So R2 and R3 are adjacent. So in the forward direction, you're losing water. And the way to think about 1,2,4 triazoles is often just to think about where are we going to lose the water. Okay? So let's take a look at two case studies. We can pick either of these randomly. How about this one on the left here? Tanner, how do you want to make it?
I like the carboxylic acid and hydrazone.
And the hydrazone. So tell me, I've got an AR1 and an AR2. Which one do you want to be the acid? Which one do you want to be?
You can make R1 the acid.
Is that what you want?
Yeah, that would work.
You think that would work, huh? Vince, you think that works?
The methyl looks like it's... Oh, no, I don't think it will work.
What do you want to do to fix this? Can we do a swap? Gee, I'm glad I didn't draw the whole thing out. There we go. you get an exchange here, and then a cyclization, loss of water here. You could have also written, without any penalty, and indeed, a lot of literature uses that prior to 2011. Why do you prefer these amidines? Well, you can avoid the sulfur, right? It's a stench. So this is a little easier. And the amidines are easy to derive. So this is just from right? Easy to make an amidine. Okay, can we do the same thing for this one? What do you say, Max? I've got an alkyl, which is that azethylene, and I've got a phenyl. So what do you want me to put on these?
Okay. Can I just have like benzonitrile? Does the Tetrazole method work with substitution on the terminal nitrogen?
So you want to use the imidrazone method. Let's think about that for a minute. So the imidrazone would be that. And then condense that with alkyl, let's say CO2 methyl. That's what you want?
Yeah. Does that work? It's not.
Sure. Yeah. The only issue is you got to make the imidrazone, which may be fine. So you've got to make your, you take your benzonitrile and you react it with the isopropyl hydrazine. Sure. If you want to use the Genentech method, you could simply take as your retrosynthetic analysis would look. There's the other way, but what Max said is fine. So you would take that, you would cook it up with the isopropyl hydrazine. The NH2 would add in here, exchange with acetic acid. And then the NH isopropyl would then lose water in a Robinson-Gabriel type maneuver to give you that. And the amidine just comes from benzonitrile. Either one is fine. What do you say there, Pablo?
When we deal with aliphatic hydrazines, how do we control the reducibility?
It's mostly sterics. And when you have something small like methyl, you can get regioisomer problems. Yeah. But in general, for paper chemistry and planning, you'll just go by sterics. When you have an alkyl group, you'll just assume you'll get alkylation on the free nitrogen. That's a good question. Okay, so how about the benzodiazepine derivative you see here? Looking for a key disconnection in problem of the day number 1. We're not covering benzodiazepines until Thursday, so we don't need to know how to make that ring system yet. We just need to know how to fuse on, annulate on that triazole. Elena, any suggestions here? For maybe bonds you want to break?
I would maybe I want to do some like a microsome disconnection.
Oh, okay. Microsome. That would give us, so if we take what Elena said in a literal interpretation, it requires that we excise here. And how do we make that? There's your midrazone.
And you can make that from
From the, sorry, can't hear you.
the aniline, so if you have the, or no, it's somewhere.
Aniline maybe eventually, but just give me one. How do I need to get this guy in, don't I? From a nitrile. Okay, give me the same oxidation state as a nitrile, but the cyclic version of it.
Where you have a halogen or something.
Okay. And where do these normally come from?
Yes,
So we can treat this with Lawson's, for instance, and you can treat it with, and then methyl iodide to make S-methyl. You could treat it with POCl3 to make chloral. Then you treat it with hydrazine, and then you close it up with acetic acid. Done. How do you make this? You have to come on Thursday. That's when we cover benzodiazepines. Questions on triazoles? Well, we'll see them later, but we're pretty much done on the intro for triazoles. Let's move to tetrazoles. Those we can cover very quickly. Tetrazoles usually either come through a one nitrogen annulation, so you take a midrazone and you treat that with HNO2 or sodium nitrate and HCl. That gives you your diazonium, which then immediately snaps shut. That's one way. Another way is a dipolar cyclizations of an azide onto a nitrile. And that's a very popular way. It's probably the most popular way of making tetrazoles. You can use a number of Lewis acids also to accelerate it. Like, I think one of the favorite ones out there is zinc chloride. I think Barry Sharpless has a paper on that one. You can do them in water. Tetrazoles are great bioisosteres for carboxylic acids. So often medicinal chemists who don't want to have an acid in their product for some reason might put a tetrazole as a replacement because the pKa is very similar and they kind of look similar in space. Great. So how do we make that based on what I just talked about here? What do you say, Steve?
The one on the right.
Yep.
I would just do the cycle addition.
Sounds good to me. And we haven't covered bridged heterocycles yet. We will in a few minutes. Any good disconnection for that? It's a pyrimidine and it's a pyridine.
From the pyridone.
So Steve says start from a pyridone. What do you want me to do with that?
I guess you could do POCl3 and then build V, but maybe a better way to do this would be to take a final ether and 2-amino-30.
That's what you want?
I like that more.
That looks good. And so after you condense that, the product is going to be And in order to exchange that NH for O, they treat it with acid followed by basic workup. But if you don't want to remember that, no need to remember that. You could just put this on a test. The two esters, you'll end up with an ester here, and then convert the ester into a nitrile by making the amide and the dehydrating. So you certainly don't have to remember that wacky thing, which is kind of idiosyncratic for that ring system, that works so well. It works so well because this is easy. This is pretty electrophilic. So it's easy to treat this with base, open it up, and then close it back. But if you don't remember that, you don't need to. Is anybody confused by that? All right, how about this one? I'm surprised nobody asked for this disconnection. Nobody wants to do a Thiazole? Tucker, you don't like that?
Yeah.
Good, neither do I. Glad nobody wants that. So, the clear disconnection, which you guys know very well now, is to just think of this as a pyridine annulating on the pyrimidine. But one wonders if 2 months ago anybody would propose that. Okay, great. How about oxadiazoles? We've got the 1,2,4s, the 1,3,4s, the 1,2,5, and the furoxane. How do you make 1,2,4s? Well, you can look at this as just simply an amidoxine. We learned already how to make amidoxine. Remember, we take a nitrile, we add hydroxylamine, you get a nice amidoxine. And then just condense that with your acid chloride, or it can be an acid with EDC, or even people have used an ester and acid. And the other way, which is far more rare, but you will see it in the literature, is a cycle addition between a nitrile oxide and a nitrile. It's weird. Rarely seen, but for the purpose of being complete, we have it here. By and large, 90%, it's going to be that. The cycle addition is the outlier. The 1,3,4 and the 1,2,5 are fairly simple. So the 1,3,4 is simply taking the diacyl hydrazine and losing water. You can lose water with Tetrazole chloride, Burgess reagent, T3P, PPA. So many things will dehydrate these things. They want to form. The 1,2,5 comes from a dioxine, and you lose water. And the furoxane, we'll see in a moment, mostly the furoxane is seen in the context of dense annulated systems. You don't normally see the parent furoxanes in medchem. That is with alkyl groups here. We'll see an example in just a moment of a benzofused version of that. Okay, great. So that gets us to this case study here, where first we need to make some key bond disconnections. What I want you to do is try to disconnect this into 3 modular pieces, where we can easily modify SAR in that sector, and in that arc. So you can do cross coupling if you like. Any thoughts there, Tucker?
Cross coupling.
All right. Give me a bond.
The first 2 arrow. Yeah, there you go. Yeah.
Okay, now what?
Do like a big.
Okay. If we do a vidig, that's going to require Who likes Vidic? Cheng, you like the Vidic?
I think you don't.
You think what? You think what?
I think you don't like it.
Oh, you think I don't like it?
Just do a condensation. Is that like biaryl positions?
What makes you think, Steve, that we could just take this system without any phosphonium and react it with that aldehyde? What makes you think that that's possible?
I mean, you have.
This is the AR group.
Yeah, it's electron withdrawn.
Okay. And what about that oxadiazole?
So I would imagine you could deprotonate that methyl. It's kind of like a 2-methyl pyridine in a way.
That methylene, you mean?
Yeah, the methylene, yeah.
So if you take the free compound, namely this one, pyridine, acetic acid, simple Canova-Nagle type, you get out the product. And the correct geometry of the olefin crystallizes out through a dynamic equilibration. Sorry, Tucker, no phosphoniums for you.
I'll live.
Yeah, but this connection you had was totally right. Because the first thing you would do when you draw out that phosphonium is maybe you would go to literature, you'd think about, oh, I need to put a bromo there, or I need to make a ketone, and then all of a sudden you realize, wait a minute, that's already pretty acidic. And it's an aldol, basically.
So then geometry is based on stereostats?
Exactly. Yep. That's presumed. One can only tell so much from the paper, but that's a reasonable hypothesis. Great. Well, the story's not over yet. We just need to make that thing now. Suggestions? What do you say, Cheng?
Carboxylic acid. And hydroxyapatite.
So the amidoxium and the acid, heat them up. Or if you want, treat it with EDC first. Make the CN bond. Either one's fine. And then heat it up. Robinson Gabriel after that. Look good? We happy? Great. How about this benzene version of furoxan up here? So clearly the first disconnection you could make
Do you actually need furoxan? Is that supposed to be oxidized?
No, not supposed to be oxidized. So it's just a reduced version of the furoxan. So I guess the 125. But you'll see in a moment the furoxan. That's the clue. A furoxan is implicated in the synthesis of this compound. So it looks like Saul has nicely volunteered to give us a route to that.
So the first retrosynthetic disconnection is furoxan, and then that can come from the...
Oh, but it's not so simple. Because, Saul, I can put the oxygen here or here. Aha.
I want you to put it on the lower left nitrogen.
Okay.
Because it's going to need to be quasi-nucleophilic. And so the electronics are better matched. Pair it to the oxygen.
Great. How do I make that?
So if you go from the nitroarene functional handle where
What do you want?
so eventually we're going to need oxidized electrophilic nitrogen at that position. And so either nitroso is in the right oxidation state.
looks pretty good. The only thing they did is they actually put the oxygen here. Either one is fine. No difference for the test or proposal. Maybe they had that isomer of the nitroaniline laying around. Steve?
Why can't you use like orthoquinone, do an oxymical, oxidize, and then condense hydroxylamine, and then do what you have on the board for 124s? Or sorry, 125s.
The only reason I suspect that may be an issue is because the regiochemistry would be wrong. So this is not you usually would put an SO2R here, and that would lead you to the nitrogen attacking there.
I guess I was still trying to say it's also compound.
Oh, you want orthoquinone?
Yeah.
Oh, sorry. Okay.
And then use like a 2-pyridine.
What's over here?
2-pyridine and 3-carboxy.
Aha. Okay.
And then do like an oxymical, right? So instead of OR, you can add in.
Oh, you want a CL there.
Yeah.
Okay, so we've added in our phenoxy unit, but that's going to be difficult. Keep in mind because it's a pyridone. It's not a phenol. So you're going to have an issue on the nucleophilicity there, whether it goes O or N. Let's say it does that in the right way. Now what?
So then you can just condense hydroxylamine
Twice.
twice.
It's creative, but the problem with orthoquinones is that they're quite capricious to actually deal with. I have first-hand experience with these in the hood myself, and normally when these things add in, as Saul muttered, they usually are going to add there. Or they might add once, re-aromatize. They're not just behaved 1,2 diketones as you would have if you were to make the dialkyl. So a 1,2 diketone where this is 2 alkyls is behaved, and you can make a dioxine, no problem. But an orthoquinone is unfortunately not so well behaved. But it's a good thought. I'm glad we put it up there. Great. Other questions on oxadiazoles? Because we're about to move on. All right, thiadiazoles. There's 4 isomers. We've got the 1,2,3, the 1,2,4, the 1,3,4, and the 1,2,5. Now the key here, hopefully it becomes clear why we're covering this in lecture 17. Because all these disconnections we've looked at so far, they're pretty much all reminiscent of pieces and fragments of things we've talked about before. Whether it be Robinson-Gabriel when we talked about making imidazoles and oxazoles. And this one is basically the same as an isothiazole. All the logic here. So a thiadiazole, a 1,2,3, we just pretend we're making a isothiazole. So it might be helpful to move the board over there, just so they can all see. So here we would take the hydrazone, and we'd just treat it with SOCl2, and we would get addition here and here, and you'd annulate on to make your thiadiazole, 1,2,3. In the case of the 1,2,4, often people will take this derivative, add it into an amidine, and that will give you R2 is equal to a chloro, which you can then do SNAR Suzuki's all day. The 1,3,4 can either be derived from the oxadiazole, which we know how to make all the way back over here. Dehydrate, you'll get your oxadiazole, and then treat that with Lawson's reagent, or P4S10, whatever your favorite sulfurizing source is, and heat, and that will transform your oxadiazole into your thiadiazole. Or, you can make it from a derivative like that. How would we make this? Acyl and then Lawson's reagent would give you your thiamide. And then just condense it with your orthoester here, and it cyclizes right there. There's your orthoester. Here it is. Or you could treat it with carboxylic acid, EDC, or an acid chloride, and then lose water. It's all Robinson-Gabriel. It's all trying to find out where are we going to lose the water. for a 1,3,4. And a 1,2,5, you can imagine from a diamine, just treating with S2Cl2, that will attack, aromatize. All right, that's thiadiazole. So let's take a look at 2 case studies. The first one is here. And let's label this to make it easier. So, Dongmin, you got any suggestions for a disconnection for us?
Can I just do the 1 to 4?
Yeah, tell me a bond.
To break between the sulfur and the...
They're numbered.
Oh, 1 and 2.
And how do you get that to go to the product? What do we do in isothiazoles? Sure. Yeah. Whatever your favorite oxidant is. H2O2, I2, whatever you like. Spit on it, wait. I mean, lots of oxidants will work. How do we make that creature? Thiourea, you said?
Yeah, but that looks like it's hard.
Yeah.
Thiourea and nitrillium might work. It's a weird disconnection.
That's what you want, Saul?
I don't know if it's what I want, but I do think that if he makes those 2 things, we'll go to the product go on.
So, an equivalent to a nitrillium might be something like that, for instance. That's fine. That may well work. It's not what they did. KNCS, aniline, H2O2. Done. That's a crazy heterocycle. Sarah, what do you suspect the next one might be best disconnected with? Any thoughts?
Starting with A and building B.
That sounds good.
Disconnecting the sulfur nitrogen. Or sorry, 1, 2.
Disconnecting the what? Super
The sulfur nitrogen bond.
Like that? Yeah. It looks reasonable until you realize you may have a regiochemical problem. And so the way they solve this regiochemical problem is they start with the bromo here, or the chloro. And then they do their SNAR. And that brings us back to that. And then this is just benzimidazole territory. We covered that already in a previous class. Thiocdi, and your formamide, and then cyclize, and then SNAR. And you are done. Great. Thanks, Sarah. Bridgehead heterocycles. Hey, Patrick, you see these things a lot?
Some.
These are seen a lot in a variety of different contexts. It's funny, 2 years ago when I asked the Pfizer people this question, they said all the time. So it's funny how the priorities change from year to year, but you see these quite a bit. Now, they have a nomenclature associated with them. And you know me, how much I love nomenclature. Right? I'm a real perfectionist with nomenclature, right? Yeah. No. So I think that the only reason you need to necessarily know this is if you encounter a patent where they refuse to put the structure. You see this a lot. So if you're very wily, let's call it, and you want to make it very difficult for someone to find out what you're doing, write your whole patent with IUPAC nomenclature and show no structures at all. It's legal. So the preference is usually to base the ring system on the 6-membered ring and then name off the 5. So this would be an imidazopyridine. And the 1,2 refers to the labeling of the imidazo. So 1, 2, and the A refers to the bond A, B, C, D, E. Yeah. You know, that's... So these are all labeled here. Here's another one. Here's 1, 2, 4 triazole 3, 4 A, because we've got a 1, 2, 4 triazole. It's connected at the 3, 4 position of the triazole, and the A bond is here, and that's B, and that's C, and that's D, and that's E. Don't need to memorize it. Just know, maybe you can go back to your notes one day and try to refresh yourself if you got one of those annoying patents. You need to figure out what's going on. That's the naming. Now, how do we make these? Do you think it makes sense at the outset, Hannah, to build up A and then annulate B onto that?
No.
Why not?
The rules say you should do the other way.
Oh, good. Yes. So for the rare people who looked at the book, the rules would tell you to do the opposite way. And also, just from a strategic perspective, it's hard to take an imidazole and find the right positions to be able to just annulate on those 3 or 4 carbons. It's hard. So if we just look at this as a building up an imidazole from a pyridine, what would be your starting material? Any thoughts?
The 2-aminopyridine and the 1,2-dicarbonyl, maybe?
What is the potential issue with that?
Regiochemistry.
What's that? Regiochemistry is a problem. For sure. Oxidation state's a problem. So what? Let's take it down a notch then. Instead of a 1,2-diketone, Hannah, what can we put in its place? Alpha bromoyl ketone. And the way you can conceptualize this is imine formation here, followed by SN2 on the pyridine nitrogen. That's it. That was easy. These look intimidating. Not to you, though. How about this one? What do you say, Gigi? Clearly, we're not going to build ring B. We don't want to do that. So I guess we need a good pyridine starting material. So I'll help you by drawing the pyridine. That's it. We're 90% of the way there. Can't hear you. What?
Nitrile. And a C1 unit.
Now, what do you want me to do to that?
Can you use like an electrophilic C1 unit? Or will that not?
Well, if we do that,
Or reduce and then use
oh,
a C1?
well, why don't you start with the reduced starting material?
Okay.
Okay.
Which one's cheaper?
Well, let's talk about that.
That's 50 cents a gram.
This one right here? Oh, the nitrile is 50 cents a gram? Okay,
No,
let's...
the mean.
Oh, you know that already?
Yeah.
Oh. You must be making a ligand of some sort. Yeah. Okay. But let's imagine all we have is coconuts and bananas on an island. And so first we take some sort of electrophilic C1 unit. So you could take, let's say, trimethyl orthoformate. It's fine. Formic acid, heat, whatever. That will give you your product. And then this compound can come from either, as you mentioned, either Aldrich, or we learned a bunch of ways of making this from the corresponding picoline. Right? You can do a Boeckelheide reaction to put an acetate there. You can oxidize it with selenium to give you the aldehyde. You can do reductive amination. Right? The value of that is just if you have different substituents here and you can't buy your 2-amino-methylpyridine, you need to have 100 ways in mind to make the amino group there. So most of them can come from that, but we might also be able to come from pyridine itself. And oxide, add the nitrile, reduce the nitrile down. All of those are fine. Super. How about this one? It's a pyrazole and it's a pyridine. And there's two arrows there. So perhaps there's a question on making one ring versus the other, or maybe there's just two ways to make it from the pyrazole or the pyridine.
Can we do one for dipolar fertilization?
Oh, that sounds pretty good. That's what you want?
Yeah.
That looks pretty good. How do we make these things?
Maybe just use pyridine and NH2 plus.
Yeah, NH2+. So our good, let's have a little NH2 plus corner. What are our options for NH2 plus? Well, we already learned about NH2Cl, but there's other ones. So you can have lots of different hydroxylamine derivatives. That's known. Usually there's nitros here. Another one people often use is the obviously these things have to be handled with care. The solubility of this thing is often limiting for metric ton scale, but you can do it on kilo. You make it in C2. These differ by their explosive properties, so you have to just handle with care and do a DSC. But this one, for instance, with an O-methoxy, has been used on process scale. So those are your NH2 plus sources. You would aminate your pyridine. You would dump in. You need electron withdrawing groups usually. And the regiochemistry depends on things like sterics and electronics. Is there another way to do this? Let's imagine you can't aminate for some reason, functional group compatibility, you just can't aminate. Do I have another disconnection I can make? Make the sick member ring? That's bold. How do you want to do that?
No, I said sit down.
Oh, make the SID known.
But I guess it's more or less along the same line. So you start with 2-carboxy purity nitrose, like the nitro group on purity nitrogen.
I'm not sure if you can make that compound. It's a good idea. It's also dipolar. Maybe the TAs can check and see if that thing can be made and do cycle additions. We'll check and get back to you in a few minutes. It's a good idea. But I think it goes into the 1,3 dipolar camp. We'll find out in a minute if that thing can be made. I've never seen that. What about just breaking the NN bond, folks? If you just treat that with a little bit of acid, snapshot. And that could be really useful because imagine you can just cut that bond then. Okay, we're in the home stretch. Questions? Let's take a look at these other bridge heterocycles. And when you start adding now nitrogens to the other ring, so we're no longer in pyrido-heterocycle territory, but now we're in pyridoxenol, pyrazinol, and pyrimidinol, things can get wacky. So here are some examples. This one, you can imagine, we could just pretend to use the exact same logic that we learned before. This one, same thing, aminomethyl. This guy here is an example of when you would make the 5. You have an aminopyrimidine. You would condense this with benzaldehyde and then add your isonitrile. And here's an example of what Gigi just recommended. Now we have a N-aminopyridazine, and we do the dipolar cycle addition. Now, before we get to problem data number 2, however, let's cover these 3 that I forgot. These can be, I think, fairly quick. Tejo? How about that one? Is that what you said? Perfect. Done. Tejo, you did that so quick, maybe you can just do the other one too. How about this one?
You adjust the camera?
Oh, Alex, you got it? What do you say?
No, I couldn't see anything.
Ah, okay. All right. I didn't forget about you, Tejo. I see where his eyes are looking. He's looking in exactly the right spot.
Can you just diazotize?
Aha. So this will give us the product. Just diazotizing. A lot of ways to diazotize. take a look at this example. You can do a diazo transfer on that, just like you would do it on a malonate. So it's very easy to convert that to that, and then immediately cyclizes. It's kind of important to know these ones because often students will propose such things in a synthesis. They'll say, oh, I'll just alpha diazo, or I'll make an alpha azido. And they don't realize there's a pyridine nitrogen here waiting to capture whatever you're doing in the ortho position. So be cognizant of that. Finally, the 1,2,4 triazole pyridine. How do we break this thing up? Like this?
Yes, oxidant.
That works.
Maybe make the amide and the hydroxy or hydroxyl.
Or this, is that what you said?
Yeah.
Also fine. Probably don't want to propose this. Not going to be so easy to make. Those are weird. With an adjacent amino here. Might work, but pragmatically it's not so simple.
So do you have
What do you say, Nick?
You have, so in the example above, you have to have this ester proof,
No.
or it was just...
So this can be made from a couple. I mean, this one can just be made from here.
Yeah.
Yeah.
Yeah, what I mean is for the cyclization, that was just as an example that you can have an ester.
Yeah, that's an example, right? So if you don't want to start, you can start with the aldehyde, but just remember this is like a malonate.
Yeah.
And so a lot of people do diazo transfers on malanates. Remember that? Like Tetrazole will do it really quick. So you can treat this like a malonate, Tetrazole it, and it'll immediately make the diazo and then immediately snap shut. And that would give you that.
That would give, yeah.
Yep. Good question. Other questions? Okay, great. That brings us then, now that you're all masters, to problem of the day number 2. Who do we have to volunteer for problem of the day number 2? Anybody eat coffee? Okay. I mean, when the TAs start yawning, you're like, jeez. It's Heterocycles, not the comedy club, folks. What do you say, Jess? Problem of the day number 2. There's almost nothing you can say that's wrong.
So first I have a question.
Yeah, sure.
Problem number, say number 2 is different from our handout. So which is...
Oh, that's the TA's fault.
Oh, yeah.
Yeah.
There are new handouts up front if you want.
The new handouts out front that are
I can just,
revised. Yeah, good question. We're going to take 2 points off the TA's score.
For this one, right? Okay.
Yeah, the real problem with the day number 2, not the imposter problem. Can't hear you. Can we do what?
Can we, like, do ring B over here?
Break the what? Can't hear you.
Ring B.
Like, break ring B.
Break ring B. Okay. All right, great. We're going to break ring B. That means we need some sort of imidazole, I guess. All right. That's what, when you say break ring B, that's what I interpret it as. How do I go forward from that? You want some substituents?
Yeah, so, having... So have the substituents all... Like the NH, yeah.
NH, okay. You want to put something there.
Like, yeah, alkyl like that.
An alkyl?
Like, aldehyde.
Oh, aldehyde. Okay. Is that going to be very stable?
No, I mean like masking. Maybe.
Like this? And do a sigmatropic or electrocyclic ring closure? Doesn't look great, does it?
Can you start from the methyl amino pyrimidine, which comes from 6-fluoropyrimidine?
Okay, Tanner. Tanner, you really like these amino methyl compounds, don't you? Have you used this one in one of the ligands already?
Not the pyrimidine.
You should. Maybe it'll work better.
Maybe. Now I know how to make it.
Now you know how to make it. There's one student in the 2017 who was in an organometallic group, and one of the heterocycles actually gave him, I think they spent like 6 months on just a ligand framework based on that. They'd never seen that heterocycle before. You can guess who that might be. Okay, there's nothing wrong with this, but hey, there's nothing wrong with what Jess said either. We just have to finish your thought. All right, there's a little clue. If you take that and you treat it with Tosmic, bless you, the product is that. And guess what? This thing can be easily removed using aluminum amalgam. So sometimes when you get into these bridge heterocycles and they've got multiple nitrogens or different substituents, the disconnection of the 6 becomes strategic. You need to know both of these disconnections. Because some of the crazy substituents you may have around here may force you into this mode instead of the one that Tanner suggested. Okay, how about this HCV polymerase from Pfizer? Problem of the day number 4. Which Nick has graciously agreed to tell us some disconnections he thinks might be good. We're just looking for some disconnections here, not the whole answer.
So we could split it into
Let's
fragments.
split it in 2. Thank goodness you said that.
Oh, I said 3 fragments.
Oh, 3 is even better. Give me the 3.
So you disconnect the CC bond next to the heterocycle on the right.
Over here?
Yeah.
Okay, let's draw
And
one of
so
those fragments.
This could be formed by nucleophilic substitution.
COH there. We can turn it into a Tazole or a chloro or whatever you want.
Yeah.
And we need the other fragment. Oh, did you want to make another disconnection? You said 3.
Yeah, the other one perhaps would be just to disconnect the pyridine in the center of the C. Yeah.
That sounds great.
Yeah, and
Now, do you have a suggestion for how I can break that bond?
which one? Yeah,
What?
would you mind
Sorry?
sorry, would you mind putting that on the?
Yeah, can you put the board up there? Maybe someone from an organometallic group, like Nick.
Yeah. So which one?
Well, the one you so studiously pointed out here.
Yeah, this just put a I guess a chloro there.
And what do I put here?
Perhaps some organometallic. Oh, yeah, that might work.
Let's use 10.
Can you just use what, Vince?
10?
Here?
Yeah.
Like this? Would it just work if we
Let's
had,
do a reductive heck.
It would
or
probably
we
be-
could just do a heck?
Yeah, the heck would be easier. Yeah.
Yes. Exactly. So that's what they do. They do a heck, and then they reduce it with palladium on carbon. I mean, I suppose you could do a reductive heck too. Okay, so all we need to think about is the way to make pieces A and B. So for A, we've got 2 heterocycles here.
So you could disconnect B
Disconnect B would give us
from like ACAC
ACAC.
and amino. Yeah, it would be. That should work.
That's pretty good.
How do you control regiochemistry?
Alpha effect. This one's a little bit more nucleophilic. So when you see these, great question, when you see these triazoles, we're going to see this again even, and you got the competition between attack here or attack here, generally it's the one next to the nitrogen that does the attacking. Great question. So that's how you
would
control
not-
what, sorry?
You wouldn't have to protect.
Nope.
Okay.
How do we make that? You might not be able to buy that. Sorry.
So just, I guess, start from the amidine.
Okay, great. We learned how to make these things back in the purine lecture, remember? Chang, right?
Yeah.
Guanylene looking thing? That's great. Hey, Nick, you moved so quickly through that. And you broke up ring B from A. Was it possible to break up ring A from B?
Well, then you would. So you would start from pyrimidine with, I guess, some sort of. Oh, you would start with 2-chloro-pyrimidine, for example.
And then what would you want to add to that?
So potentially, could you have amino then?
This type of thing?
Yeah. Well, I was thinking you had something like an aminopyrimidine or chloropyrimidine.
Yeah, adding it to the chloropyrimidine here, yeah.
Yeah.
Sure. I mean, if you want to propose something like that, and then oxidant, you can do that. Sure. The way they did it was just as Nick said in his first instinct, which was to build up the triazole and then condense upon that using pyrimidine logic, condense upon that to give with ACAC to give the product. And B is just a pyrone-looking thing. And the first rule of pyrones. Does anybody remember what the first rule of pyrones was?
Add water.
Add water. That's it. If you add water, that rule will never let you down. There's my water. And once you do this, we officially defer this to other faculty at Scripps to help you. So you homologate to there. It cyclizes closed. Tons of ways of making these. They made it racemic and then did a chiral step, but you can also do asymmetric pathways to get to that type of thing. Close it shut. And alkylate with the corresponding Thiazole or chloro, whatever you want. And you get out your product. Do you know Martha, Patrick? Is she still there?
Yes.
So she worked on this. Did you know that? Yeah. Yeah, 2 years ago, one of the people who were here is actually an inventor. It didn't. I don't think it went on to become a drug, but they co-invented this compound. Okay, great. How about quinolizoliums? Those are represented by problem of the day, bless you. Problem of the day number 3. So let's take a look and see if I've got this right on the board here. So problem of the day number 3, Cheng has nicely volunteered to help us with.
Oh, sorry. I need to think about a way to make this compound.
Yeah.
Okay.
I'll help you by drawing that for you.
Breaking the A bond and then the bond parallel to the A bond. The natural company of and then put the substrate on the 2 position.
And then what is my starting material?
Beta hydroxy diester.
Right, the same building block we used over there. You don't normally see just a quinazolium like this. This is the parent ring system, but you do see things like this all the time.
So you treat the compound with PO3 and then you do the...
And then you could make the quinazolium, yeah. That would form. How do we make trazodone? I need the... we're looking for a 5-second retrosynthesis. Max? 5, 4, 3, 2.
Okay. 2 amino pyridine.
2. I couldn't hear you?
2 amino pyridine.
Plus Say that again? What?
That's the issue.
Why not just say 2 hydroxyl purities plus CDI?
There we go. Thank you, Saul. The 5-second retrosynthesis of Triazole. How about this DPP4 inhibitor? This is a fragment, I believe, of Januvia. And you probably have family members or people you know that take Januvia. It's like $1 billion drug, amazing story associated with its synthesis and how they put the stereocenter in. First doing resolution, then doing hydrogenation, then doing biocatalysis. It's like a big deal. A lot of papers. But we're going to cover the boring part of Januvia. Saul, do you have any ideas?
I want to start probably from trifluorocetanitrile.
And
Thanks.
trifluorocetanitrile.
Sorry, if you're going that way, then you want to...
Well, you tell me which way. This way? Yeah?
That's fine, and then start from trifluoroacetic acid.
Okay.
Or I think you can oxidize the aminopyrazine, which is what I was saying. For trifluorocetanitrile, add 2-aminopyrazine and oxidize the nitrogen. It's net same. You intercept the same intermediate.
Okay, let's just go with this one. How do we make that?
SNAR on an activated pyrazole. Or not SNAR. Nucleophilic addition.
Kind of what Elena helped us out with at the beginning of class, right? When we did problem day number 1. What if I told you you could make this compound in an even easier way without the protecting group here? What if your protecting group was oxygen? It's rough to get these in there right in the first time. Okay, there we go. What if your protecting group was right just an oxidation away? How could I go from here to the product?
Under acidic conditions, that should be selectively reduced.
Yes, perfect. And now we're just starting with the pyrazine, a 2-chloropyrazine. Take 2-chloropyrazine, add hydrazine, then TFAA heat, and then some acid, palladium, will selectively reduce the left-hand side, not the right-hand side. It's harder to protonate this right-hand side, so you'll get a little protonation there. This is kind of not very aromatic at all, this portion, so it's easy to reduce that part. And so your protecting group is just O2. Questions? All right, in the final 15 minutes, we've got just a couple of small things to cover. So the first one is this dimer that's linked by a pyrazine. So first we need a deep thinker to tell us how we might be able to dimerize this rapidly and take advantage of the innate functionality.
Start from the formal arene and make it pyrazine.
We could take it even further. If you didn't even want to start from the formal arene, you could just start with the arene, formaldehyde, and the pyridazine, or pyridine. So pyrazine, formaldehyde. You make your double manic. This is pretty electron rich. Adds in twice. Out comes your dimer. We already learned how to make this type of ring system annulated onto there. If you go all the way back somewhere around here, we should be able to get to that. Cheng is shaking his head, meaning he knows exactly what's going on.
Using Hannah's disconnection.
Using what, sorry?
Hannah's disconnection. So I just have a... alpha bromoketo. That comes from also this also hydroxy aniline.
Aniline.
Oh, sorry, not aniline. Just cyclohexanol.
Perfect. Take alpha hydroxy cyclohexanone, cyanamide, and heat. You'll get the amino oxazole. Then treat that with your alpha bromoketone. You'll get your imidazole linked to an oxazole, which then is electron rich enough to do manic directly. But if you didn't know that, you could do what Saul said and formulate followed by reductive amination. That's just fine. All right, the next one. In the home stretch. Tejo, you're very close. Care to give us a disconnection? N-alkylation. You mean N-arylation? I don't see where. I don't see where you're alkylating. Oh, you're alkylating here. Where, what do you mean alkylation? Tucker's giving me the eye. That means he must know what's going on. You're going to come in for the assist?
Break B has COBA 4 chloro 3
Pretty good. So we would turn this into the S-methyl or the chloro, whatever you want, just like we did all the way back in Elena's problem. And then we did it again over here, and now we're doing it again over here. Turn the amide into electrofuge, add in here, and then it'll snap shut. That 4-chloro is pretty activated. Should we cover this one? Does anybody care how this is made? Hannah wants to know. I suspect it. Yeah, you can do it asymmetric or not. Asymmetric, I think they do it with a copper catalyst and an oxazole in it or something like that. Yeah, just asymmetric Michael to a vinyl nitro. Yeah, those are known.
I've just never seen people do it with copper. That's all.
Oh. Yeah, tons with copper. Yeah, I mean you can use ureas or whatever as well. Yeah, sure. And then here you just formulate and add in the presence of allylamine. Gives you al there. and then treat that with base, and you decarboxylate the other one. But that's more someone else's problem, not heterocycles really. Desaturated heterocycles are mainly the logic you learned in other classes. Problem with number 5 is a famous old cyclization. This was done by Dow on metric megaton scale. It's an old cyclization known as the Tissler. So problem with the day number 5. Last one with 7 minutes remaining.
Is there some problem that I'm missing with starting with trichloroperimidine and doing 3 sequential SNARs?
Oh, the problem is not, problem with day number 5 is not how to make that. Problem with day number 5 is...
Oh, the mechanism of cyclization.
Yeah, when you heat, we're going to get to that in a minute. Sorry. When you heat this thing up, how do you get that? That's Tissler.
You make a nitrate that then gets quenched by the purity nitrogen. So you can imagine kicking electrons down from that nitrogen onto the other nitrogen and then expelling CO2 to make a nitrate. Bond and protonation, and then isomerization, or I guess tautomerization to the aromatic ring.
It's a reasonable thought, and the only thing is that there's an intermediate you can isolate that supports more of a stepwise mechanism, but I don't think there's anything wrong with proposing that, because I'm not sure, even if that the intermediate we'll see in a moment, you could still imagine some sort of nitrine. But what might be an intermediate you get before you even get that?
Can it be 6-pi first?
6 pi where?
If we rotate everything more, moving carbon nitrogen with the acid group on it up.
I like 6 pi off the carbonic oxygen personally. Or I guess it's 3-3.
So am I drawing this right?
Yeah. And acid.
Okay, now I've redrawn it. Now what do you want me to do?
Wing wall long pair on the nitrogen on the central one. Oh, yeah. Then we can formally draw 6 pi and then N1 will form. With the plus and nitrogen.
To give you a plus and nitrogen as a product?
Correct.
This? And then ethanol comes in and just... How do we get that NO bond cleaved? I guess it's lost to aromatize? Is that the idea?
Most of the city has
Yeah, I gotta say, you guys are very creative. What ends up happening in a Tissler cyclization, at least what they know for sure happens, is that you get attacked there. That's for sure, because they can isolate that intermediate.
to give us a cool heterocycle. And they lose CO2, and that's the product. That's it. Now we're ready for what Saul pointed out a minute ago. What he thought problem with the day number 5 was, is how do you make that? And he said, why not just start with a 1, 2, 3, or 2, 4, 6 trichloropyrimidine? That would imply you need something like this. Plus something like this. Is that what you want, Saul?
Sure.
Don't sound very, very confident there.
I mean, it's pushing the limits of electron richness for SNAR, but
Yeah.
I think it's okay.
Yeah. Probably better off targeting something like making this instead from the aminopyrimidine. If you treat this with ethylchloroformate, you'll get that out. And this kind of recipe will work for you. Adding hydroxylamine into a derivative like that. Or, even better, you can also make it from the addition of this chloro with cyanamide. And then add hydroxylamine to that. Either one is fine. If this is confusing, good. This is lecture 17. It doesn't get any harder than this. So that's it. If you're confused by this, but everything else is fine, good. And we have, unfortunately, run out of time. However, it looks like you all are so bright-eyed and bushy-tailed that you really want to know what's going to go on with this one. So I'll just give this to you, that retrosynthetically, this comes from a Vilsmeier-Hack formulation, and this comes from a reductive emanation. And that gets us back to that. When they take this with the methylpiperazine, 2 equivalents of that and 2 equivalents of butylate. First equivalent of butylate deprotonates here. It then adds into the aldehyde. It also activates through chelation this bromide. The second equivalent then adds in. And this compound can be made using, I guess, what we've christened the term the Hanna disconnection. Plus so
1,1,3 trichloroacetone. 1,1,3 trichloroacetone reacts with this to give you the dichloro here, which after HCl treatment gives you the aldehyde. You then do the amination. You then do the Vilsmeier. You do the reductive amination. You do the Vilsmeier formylation, reduction, and you get out the product. You can imagine the reason they did this stepwise is that it would have been very difficult to just use alpha bromoketone here, right? How do you get the regiochemistry? It would have been a disaster. Questions? All right, cool. So we have a couple days to recuperate, and we'll see you on Thursday for benzodiazepines.
Did it work? Did it work? You tried this thing on?
I
Yeah. Yeah. Oxy for, so we go, normally we do this is actually just from urea. You buy this, and this comes from urea plus melanin.
Okay. But then you say you have
No, it's going to go here first. Well, I think it would go methoxy here first, methoxy here first, and then here. If you use Suzuki, it would go here, here, here. But nucleophiles that are X stage, here, here, and here.
So this is not more.
Depends. For Suzuki, it goes here second.
Okay, second.
Yeah, for palladium, you go here second. For just regular additions, into dirt, you go here and here first.
And for just SNR, you have to go here.
So it's there first. Yep. We covered that already. Yeah. TAs, am I telling them right?
Yeah. Oh, it's like because it's like a 4.
Yeah. Yep. What's cooking, Sam?
I'm trying to make a 1, 2, 4 Oxadiazole for like
Which one?
room.
Where is it?
This, and I can get like less than 10% if I do it one pile of T3P and TA. But even if I try to just make it stepwise with that too, it's like mostly like converted acid.
When you have this compound and you cyclize it, is that clean? With this in hand, is it clean?
I haven't tried just cyclizing this because it's going to be half acid and that I don't care what it.
But even the mixture, to understand if your conversion here, if there's no reversibility, is what I'm asking.
Oh, I see. It might be. I haven't tried just like subjecting this to T3P. T3P was the only thing that I got to actually cyclize it, and then I was just doing it one part. Because like I don't know if I'm getting like degradation of the cyclines, but like acetic acid and everything else was kind of just like obliterating when I started with it.
Yeah, so
I wonder if you instead use the disconnection we talked about before.
I don't know why. I tried to
And then added
Because
hydroxylamine. I bet that would work well. The other thing that might work for you is the Genentech disconnection. So you could just take super stable acyl amidine. This is stable. Now normally you treat this with hydrazine, you'll get the triazole.
Right, that's why.
But if you just treat this with hydroxylamine and acetic acid, it should do the same exact thing.
Okay.
Right, so the logic we use right over here for 1,2,4 triazole, it's the same if this is oxygen.
Okay. Yeah, I tried acetic acid and hydroxylamine. I thought with this intermediate. That's the first thing I did with
hydroxylamine with
Oh, the I see. That's why. And that did nothing, but I guess not as high.
which did you try with hydroxylamine?
Oh, I tried this as the oxy with the oxy here.
But I thought you
I subjected this to
the mixture.
Yeah, to acetic acid and hydroxylamine, and my materials just kind of like.
Oh, you don't want hydroxylamine? Yeah. So you don't need excess. Why would you add more hydroxylamine to
It's
this?
in the prep. I don't know. I looked at it afterwards, so it's like this kind of garbage prep, but.
But this is probably going to be a good prep if you don't mind the stench. It's kind of
guaranteed you'll be able to make. That you can make.
Okay.
And then, or this one is easily makeable, and I mean that should be clean. This is straight out of the anti-JOC. You can actually make these. You don't need to isolate them. Then add hydroxylamine to that with 10 equivalent acetic acid.
Yeah. So,
The only other explanation for why things might be going to garbage is that.
Yeah, that's kind of
Because these are sensitive to acid. So if I were you, I would practice my prep with R equal to methyl or phenyl, so that you know, is it you or is it this? Because everything are notoriously unstable to acid.
Yeah.
And they open, and then you've got the Bach there as well. So this looks like a problem of this part and not this part. And so if that is the case, and you are desperate to make this compound, the issue is that, one other idea would be to just, can you put this guy on after that one is all there?
I can try it. I think it was just like, how do you make it some bromide?
Well, but you're using your chemistry, right?
Yeah.
So the benzyl bromide can just come from, why don't you just do towel? Oh, you're worried about bromination here versus here. I see.
So this one, you'd say this one's good.
Well, why not just use benzyl alcohol?
That's not good to position.
Then apple.
Oh, I see. Yeah.
That should work fine.
Okay.
I think that's probably what's going on, Sam. This guy, and then bromide, and then use your chemistry. This shouldn't interfere with it.
No. Okay.
I would maybe practice on that, because if it doesn't work on this, it means something's wrong with our prep. And if it does work, you can just use the same thing to get to the product and not have to worry about the incompatibilities of that under acid. I think that's probably what's going on. Yeah. Let me know. Yeah, hope that helps. Yeah.
SNL goes to side, and middle, and side.
Side, middle, side.
Right. And it's Suzuki side, middle.
Okay.
So the middle is last
In Suzuki, and then for SNER, right with a heteroatom, it's side, middle, side.
Yeah.
Yeah.
To clarify, I tried to look up and rationalize why it works in that order, but I couldn't really find a good reference.
Maybe chelation to palladium. That's how it reverses, maybe.
Can I just clarify